So I'm Nick. I'm going to talk to you about RISC-V. And RISC-V is an open source modular ISA, which probably doesn't mean anything at this point. Let's start with the last part. ISA means instruction set architecture. It's basically a specification, a document that describes the set of instructions the CPU understands and the context under which those instructions are being executed. So previous memory, virtual memory, and the memory model, and lots of small technical things. Basically, it's a specification that we give to a hardware designer with CPU and to the software designer with hardware and an operating system and the whole software stuff. What is RISC? RISC stands for Reduced Instruction Sets. Now, this goes way back. So, when was the last time you used a scientific calculator? If you remember that it has a few big commands like square root, power, inverse power, sine wave, hyperbolic sine waves. It even has a button that plots you stuff. So those are very complicated commands to execute, right? But when you have a small screen and you need to write your expression there, this makes sense. So back when we didn't have enough memory was very expensive. I mean, in the 70s. CPUs were designed like that, were more close to what your scientific calculator looks like and less looking like something that writes lots of code, right? And people actually wrote in assembly. They wrote words in instruction of the CPU. We didn't have higher level languages like Fortran, C, compilers hadn't involved much. But basically, it was that memory was expensive. So in order for programs to fit in memory, they needed to be small. Much like the screen you have in the scientific calculator. So the instructions your CPU provided were complex instructions, but that's why we call those whole processor of complex instruction set or CISCs, complex instruction set CPUs. Okay. When memory became cheaper and the compilers evolved and we have more area to work, and we could use higher level languages to express programs and then having them translated, having it all translated in computer, in CPU instructions, things changed. We started having, the new concept was that your CPU will do something very simple. It will give you the basic instructions to play with. And every complex program you will express in those simple instructions. This is very nice because it allows us to have simpler CPU designs that can be faster and they can be more efficient. If you think about it, let's say you have a chip there, it has some circuitry to calculate the sine, and you never use sine. You have all the circuitry sitting there burning power, which is not efficient, right? But if your CPU only gave you this bare minimum, then you could express any instruction, any command, any complicated program that you want, and you use your CPU all the time, you wouldn't waste any energy there. Also, you wouldn't waste space, right? Complicated instructions take space in the chip area to implement. When you only provide simple instructions, you can make smaller and more power efficient designs, and you can fit more cores in there, which is better than having one complicated core. It's better to just get 10 of those in the same area, right? So this approach proved to be much better than the previous one. It started in the early 80s, late 70s, if I'm not correct, if I'm not wrong. So, the moment it arrived, it gave like 200% performance compared to VAX, for example, which was the main thing at the time. We don't see RISC CPUs in our desktops because our laptops, desktops, and servers are mostly x86. It's the architecture started by Intel at 1978, and now it's maintained with co-maintained with AMD. So there's only two companies to make CPUs with these architectures, and the reason we have it on our desktops and laptops and servers is basically because in the 80s and the Windows boom, and we had a lot of applications written for those CPUs, so we started it. But at the same time, if you checked out high performance computing, they were mostly RISC, right? IBM Power architecture, for example, is a RISC architecture. And nowadays, RISC architecture is actually very common. We have them in our mobile phones. especially because it's very power efficient, right? Your mobile phone needs to, the battery lasts the whole day. If you had a desktop CPU there, that would not be possible. And it's also faster, much better than x86. If you have, I see you have the new MacBook laptops. Those laptops have ARM processors inside. They have RISC processors. They just have RISC processors and allow them to burn a bit more power, and they are very performant. They actually are better than the x86 processors that are allowed to burn the same power. If you give them even more power, if you allow the power budget to be larger, and you use those processors at the server scale, then it's seriously good. So so RISC is more power efficient. It's simpler to implement. We can stuff many processors there, and it's already we're already using it. And okay, x86 is evolving because, and Cisco is evolving because of the way we print the chips, right? We reduce the node size, we make them smaller and more power efficient, the implementation, but not the architecture. We are going to hit a barrier at some point where we won't be able to shrink them anymore because of quantum physics. Okay, we cannot make tiny subatomic transistors. So at least not as far as I know. So this will stop at some point, and then when we reach this state that we won't be able to shrink the CPU anymore, we need to use a different architecture. So RISC is the future. But it needs to be a modular ISA. Okay, think of it like this. Right now, you go to the market and you can either buy a warehouse, a nice house, and a hotel. You cannot buy anything in between. When you go to Argos, for example, to buy a microcontroller because you're building a fridge or a coffee machine and you want a small microcontroller there to do the timings, you'll get an ARM CPU or something very simple. If you want a desktop, if you want something more complicated for IoT, then again, maybe there's a bit more complicated CPU there you can get, like a small simple house. But then you go to the desktop and laptop and you get a really large house with swimming pools and everything. You cannot make it smaller. And when you go to servers, you get the whole hotel. Even if you use only part of it, even if you don't need the whole facilities, if you need something different, you're going to use only a part of it. You don't have options, right? We have two architectures right now. We have x86 and ARM. x86 only gives us desktop and server CPUs, with a lot of features that burn a lot of power that we don't want all this functionality most of the time. And to give you an idea, we have these beasts and we still use GPUs, for example, to do our calculation, because this thing, it burns power and it still doesn't do what we want, right? And then we go to ARM, and ARM gives us some very small cores, for things like coffee machines and fridges and toasters and stuff like that. And then it gives us some bit more complicated CPUs for IoT, like cameras, the projector, for example. And then we have the application class processors, which is what we have on our mobile phones and what we have on your laptops. Nothing in between, okay? Nothing in between. We only get the choices to get specific packages. Imagine a different scenario where we design rooms, okay? Instead of designing the whole site, instead of selling you the whole building, we give you a selection of rooms, and you can choose which rooms to use in your setup, depending on your needs. You may want to build a restaurant, you only want the kitchen, you don't want the bedroom, for example. So you can check out whatever you want and create a CPU suited for your needs, meaning that the part that you're not using, the part that will burn power otherwise, sitting there, will not be there. You get a much more efficient design suited for your needs. You may need privilege separation, for example, to go to the technical stuff, but you may not want virtual memory, just want separation of processes, right? Maybe you don't want floating point. You only do integers. You don't need floating point. If I have an NPU there sitting. With RISC-V, we give you, instead of giving you packages, we give you the rooms, and you can check and create your own configuration depending on your own needs. This is new stuff, okay? And it's not just the design of the hardware that allows you to do that the hardware basically is the specification, because we don't provide the hardware, we provide the specification. Gives you a set of extensions, and you choose which extensions you use that you want. The basic extension is integers. You get RV32 and RV64i, which is the integer set. You get your normal add, sum, and stuff. Multiplication is a different extension. You may not want to do multiplication, right? So, and then you got floating points, double, quad precision floating points, vectors, atomics, depending on what you need, you can add stuff there. And the software stack, the compilers, the assemblers, are also built this way. So you can compile your program and say, hey, my hardware doesn't have a floating point, so I don't add floating point to the compiler. And when the compiler needs to emit floating point the instructions, it will add there some simulation, some software emulation, both for the rare case that you need floating point in your system. So so software compensates for this modularity. And again, the operating system itself will, the Linux kernel, for example, will patch itself depending on what functions your CPU has. So it will work with a base. We have a bare minimum that is needed to run, for example, Linux. And then if you have extra features, the Linux will patch itself and provide you with those features. What it means to be open source. So again, this is very new. Traditionally, the instruction set architectures were designed behind closed doors in some companies like Intel, AMD, or ARM, or IBM, or digital, or whatever. They were not discussed in public. Okay, it wasn't something that was created by a community. And when they were designing them, they had specific needs in their mind, specific use cases or marketing practices. Okay, and they added stuff there that was not there wasn't a technical reason, but it's so nice. Okay. So we ended up with an architecture like x86 that has a lot of baggage there. It has a lot of legacy stuff. Our x86 CPUs, they have instructions that we never use. We literally never used since the 90s, and they are still there for backwards compatibility. They're burning power for no reason and adding complexity to the system. This is what you get with, I mean, with RISC, you don't have that because you don't provide basic stuff, right? You provide simple instructions, not complicated stuff. So chances are that you will keep using them. The thing is that open source allows us to design something altogether, and many experts from different fields and from with different backgrounds, they come together and they contribute to this stuff. And this becomes much more mature. This can become much more mature and much more generic, and allow us to have a much better coverage of use cases with our systems. It also means that you can use this without paying a few $1 million. Now, if you want to build a chip and you want to have a processor inside, you either have to license the x86 architecture from both Intel and AMD, which means some millions of dollars to both of them, which is not going to happen. That's why we have a monopoly on x86, and only Intel and AMD print x86 chips. Or you go to ARM, and ARM has a much more flexible licensing model. That's why we see ARM CPUs built by Apple, by Qualcomm, by Huawei, by MediaTek, by lots of companies. They license these cores from ARM, but again, they need to pay millions. And not only they need to pay millions, they pay millions to get this schematic or this specification that they cannot touch because it's owned by the company. You cannot add your own instructions there. You cannot modify them. You cannot extend it. You have a very limited flexibility, set of things that you can do. RISC-V is open source, meaning that, okay, you don't need to pay us millions to use it. You only need to be a member of the RISC-V Foundation, RISC-V International. If you want to market the RISC-V CPU, you have the logo there and the name. If you just use the RISC-V CPU in your product, you don't need to tell anyone about it. You don't need to be a member of the international, just use it. Okay? You can also modify it, add your own instructions there, add your own functionality, things you need. Something that previously was done with accelerators, right? Because people could not have stuff in their CPUs, what they did was you have a separate chip that would, for example, do FFT or do, I don't know, would accelerate the processor like macro applications or neural nets or AI, separate chip. because you couldn't put it inside the CPU. The CPU is, even if you buy it, if you get the design, get the spec, you cannot touch it. On RISC-V, we urge you to play with it. Okay, you are free to play with it. You are encouraged to play with it, and you are encouraged to give us feedback on and help us standardize it. So if you think of a good, of a nice idea, and you put it there, and it works, you can come back with it, file international, propose it, talk about it, it may become a standard and be used by others, which increases value of this spec because it gives a lot of you have there's a lot of opportunity there for people to innovate. Why V? What happened to the previous four? So that's a short history of RISC. So as I told you, it started in the early 80s. RISC and RISC-2 were designed by Manuel Stratenis, the founder of our lab, while he was in Berkeley. SOAR and Secure, there were two experimental processors in the 80s for really experimental purposes. And then we have RISC-V in 2010. Again, started in Berkeley as a student project. And they decided that to open source it, to share it with others for educational reasons, okay, help them teach computer architecture. And in 2014, the base spec, the integer spec frozen, and basic privilege stuff. And then by 2015, we have RISC-V Foundation, an organization founded to manage the specification. And when US started the whole thing with sanctions against China, we moved it to Switzerland, to neutral ground, so that we can keep working together without this mess. And we now have RISC-V International, which is an organization, the organization that manages the spec. It's a member of the Linux Foundation, which is a much larger organization handling open source products. Okay, what's the impact of RISC-V? This is an old slide, okay? This is last year. Last year we had 3,100 members. This year, I know for a fact that we have at least 3,400 individual members. I mean people, okay? Because this number includes organizations, includes companies and stuff. So this is larger now. I mean, it's at least 300 members more, maybe at least 300 members, at least in the slot in the community individual category, but it grows fast. And those are the people that contribute to the spec, okay? We are talking about individuals like engineers from people that are passionate about this, academics, research centers, and small companies, startups, people that have ideas. They may come from a larger company, they may have a background, they may have some history in the field. And then we have larger companies, and we end up to the really ones. Okay, Google, Facebook, Microsoft, Intel. I don't know if Microsoft is another, but Google, Facebook, Intel, Samsung, Huawei, Alibaba, Micron. I mean, lots of companies, and there are some really big companies you don't know about because there are companies that design tools for designing processors. So they are the tools that Intel, AMD, and the others use to compile their processor code, and so those are also also some other companies that design subsystems that are very popular. We've never heard of them, but they're everywhere in every device you have. So every big player is there. Okay, they are all there. They're working together, and it's awesome. And it's already being used in many places. Okay, you have an NVIDIA GPU, you have a Falcor, you have a chip inside, the microcontroller that handles all time critical stuff. And which is the reason why the NVIDIA is open sourcing their drivers, is because they moved a lot of functionality they had in the operating system, they moved it to the GPU by using a RISC-V port. Seagate and Western Digital, if you get a hard disk drive for Seagate or Western Digital, which basically is most hardware these are there, you have a RISC-V microcontroller in there for storage. You have a Google Pixel phone, like I do, it has a Titan 2 chip, again, a RISC-V chip, it has a visual port, again, assisted with RISC-V. Samsung is using RISC-V in their designs, as subsystems in their SoCs, in their phones, in other systems. Huawei, again, seriously invested in RISC-V for various stuff. Not yet, they're mainly using mobile phones, but again, subsystems. because it's open source and because people don't need to tell us about it, okay, there are lots of implementations out there we've never heard of. We know for a fact that they're using RISC-V in those small Bluetooth headphones, like buying billions of those, various subsystems and various microcontrollers, you know, around your car, around your mobile phones and laptops and everything. We have a few single board computers, those think of them like Raspberry Pis. We have them for development right now, they're all not very powerful and they miss the functionality we are working on. I'll tell you a bit about that later. So we use them mainly for development and playing. It's not really powerful system. Networking equipment. We use it for RISC-V being used in switches, routers, you know, stuff like that. And a lot of things we don't know about, again, because they don't have to tell us about it. It's open source, they can use it and don't need to tell us anything. Before we lost count of how many RISC-V core implementations were out there. Implementations, I mean, CPUs using this architecture, both open source and proprietary, because we have some open source implementations that you can download, compile, and put it in FPGA and play with them. And we also have proprietary. Before we lost count, because there were too many of them, that's a link there 2 years ago. There were already a lot. And by 2022, we have an estimate about that we're about 10 billion RISC-V systems out there. And this is a more marketing slide about the projection. We expect to have 8 billion RISC-V CPU cores by 2025, and this is a conservative approach. You see that it's mostly on IoT, industrial, and automotive. And that's because the features we have on the chips right now, they don't include features needed for more high performance or scientific or desktop class CPUs. But we have them there. It's just that we don't have chips printed with them, because from designing something, putting something in the spec and providing with people with functionality and all the software, everything they need, they still need up to 2 years to actually print the chip with that. So there is a delay, okay? A few highlights before I move on to see, again, to give you an idea about the impact of RISC-V. MIPS, a very popular CPU architecture used in routers. The company that owned it said, screw it, I'm switching to RISC-V. So IBM, they open sourced their power architecture. The power architecture is a very popular architecture. It's been used by top 500 supercomputers for a long time. It's a historic thing. It's been used in mainframes, very powerful, and it's a RISC architecture. So again, IBM, they open sourced it, they open source power, because now they have an open source rival, which is RISC-V, and they say, okay, even though they open sourced it, people still prefer to work on RISC-V. So IBM joined RISC-V and is working with us. So basically, IBM endorses RISC-V from now on. Intel invested $1 billion in RISC-V. They did that because now Intel has a split in two. They have Intel, the part that designs CPUs and chips, and they have the part that is leading the fabs that Intel fabricate. So Intel Fabs is now a separate company, and they need, and they expect to have a lot of clients, and they expect that most of that. So they provide chip printing services to third-party vendors, like not only Intel and printing Intel Fabs anymore. So they expect to have a lot of clients, and they expect most of them to be RISC-V chips. So they invest in RISC-V to have good relations with their clients. They set up a lab with BSC, and Apple is playing with RISC-V. We don't know what they are doing exactly. There are some leaks there that some of your laptops may already have a RISC-V microcontroller in there. But Apple is very secretive on what they're doing. EU through the CHIPS Act. CHIPS Act is a 15 billion investment that the EU is trying to push forward for development of chips. They promote RISC-V. They've already invested hundreds of millions for RISC-V CPUs for high-performance computing. There is also the European Processor Initiative, a project to create a European CPU that includes a RISC-V accelerator. We'll have it running 100 meters from here. You can see printed through the ASIC. And we have both NASA and ESA creating chips for space. So ESA has Nodal 5, which is an ecosystem around RISC-V for CPUs meant for satellites and everything, lots of systems. NASA is working on RISC-V SoC. mostly for, initial design for space applications, like high performance, and it's not very, high power, let's say, space applications, and they are also going to put stuff there and use this chip for government stuff. So you have a chip that is very trusted, for security reasons, designed by NASA. So lots of money there, lots of investment. India and China are also heavily invested in RISC-V. We have like Alibaba, we have Huawei, we have not only companies, we have academic institutions as well. Investing in RISC-V, Shakti processor, which I have India, they have a lot of series of processors. Right now, because I told you that there is a delay between us designing something, putting something in the spec, and a chip being printed on, there are a lot of HPC systems being designed around RISC-V. Now, this is the technical stuff. I'm not going to waste your time with this. This is just to show you the progress of the project and what extensions we've been working on. Lots of them are related to things that are not really interesting for Argos, but a few of them might be useful to you. So, for example, we have a precision floating point, and that's the real deal, okay? It's not this messy thing that Intel has with 8 bits. No, this is the real deal. This is a 128-bit precision floating point, the thing that Power had, the thing you find in very massive systems. And it's IEEE compatible. It's like it uses the proper format for that precision floating point. We have a spec for that. We have a beautiful vector extension. So on x86, for example, each time you get a new vector length, you get a new instruction. So we have 256 vectors, now you have 512 with AVX, then you have, so every time you get a new vector length, you need to recompile your code to take advantage of this. Not in our case. In our case, we have variable length vectors. This allows you to compile your code once, and depending on what's the vector length of the machine, you just use it without recompiling, because the code itself is designed to, it has this notion that vector length is variable. How large can vector be? It's up to 64K per vector register. That's huge, okay? Intel is now, I believe, in 1024. That's their best vector length. We can go up to 64K. And actually, as I mentioned, we have a chip a few hundred meters from here, the part of the EUI, the European accelerator, the European processor that does vector acceleration. And our vector length is 4 kilobytes already. And works, okay? It's up to 1 gigabit at this point. It can do integers, it can do floating point, it can do fixed point. Fixed point is used in signal processing a lot in media codecs. Fixed point and multiply accumulate is a very common instruction used, a very common process used in coders. There are other cool stuff about the vector extension, but I don't want to get much into detail. We are working on DSP extensions. We call this packed SIM. Again, mostly fixed point arithmetic for accelerating encoders, but you also get complex multiplication somewhere in there. Maybe not what you would want, but it helps you, it will help accelerate things like FFT and other processes. It's 32-bit imaginary and real part. But we can work on other things as well. I mean, this is still being worked on, okay? It's a work in progress. And as I said, this is open source. You may join and give us, share your ideas, give us feedback about who you want to be in there. There is also a group, there's also multiple groups that are also multiple groups that are working on AI, neural networks, machine learning, and graphics extension to accelerate such workloads in the CPU instead of having, it's not requiring an accelerator like another chip to do that. And you can find, this is a link there to our specification status page that will give you an idea on what we are working on. Before we go, I'll give you an idea of what's our job, RISC-V, what we are doing here. So we have a very active in the project. We don't just use RISC-V for the projects we are involved in, European projects we are involved in. We contribute to RISC-V. We started by contributing on security. I used to be the chair of the Trust Execution Grant Council. I'm the chair of the runtime integrity special interest group. A special interest group is an umbrella of task groups within this technical committee. And I was also the elected representative for community and individuals members into the technical steering committee. So it's the committee that governs the technical committee and decides what goes in, what doesn't go in. So very involved in RISC-V. George Christou, another colleague of mine, now Dr. George Christou, he worked on control flow integrity. It's a very useful feature. It's a requirement to run RISC-V, to run Android on RISC-V, for example. And Vasilis Papastathou, a professor in the computer science department, was the acting chair of the IMU task force. And IMU is a very useful system that, for example, you use when you go to a data center and you say, I want to give me 2 GPUs and a network card assigned to my virtual machine. So it's a way of assigning, among other things, assigning devices to systems. Here are a few contributions, a few of our contributions. For PPMP, I was the author, and George is the author of Control Flow Integrity, and we've contributed in a lot of them. So we are part of the spec, right? Our work changed the spec, and the community recognizes this. I mean, we have an impact, we've got awards, and you can see there in this table, lots of large companies are in there. Google is there, Intel is there, lots of, and in the end, the final plan, it says fourth. I'm not showing this slide to brag about it, not just to brag about it. I'm showing you this slide to give you so that you understand that this is not a closed club. This is not only for big players. This is not a playground where only very large companies may have an impact. We can all have an impact. If you go there, you have ideas and you work on them, you will have an impact. This is an open source project. Okay, lots of players in there, from the whole range, from really big companies to a small institution in Greek, right? So I urge you to join and help us and give us your feedback and your expertise, and help us make RISC-V better and better suited for your applications in scientific computer, because we don't, we rarely see, we don't really, through the whole design of CPUs, it's not that the companies have a very good relation with their users, right? They didn't get this feedback. In this case, we can do that. You can help us test ideas. You can help us with your code and data to profile our stuff and optimize them. So there's a lot of potential there, and you may end up in the news as well. So please join, and I hope this wasn't too boring.
Thank you, Nick. Any questions from the people online? So I have a lot of questions, but probably some of them.
Don't worry, you can
go offline. I was wondering, like for instance, the RISC-V systems that we have here. I mean, what is the, first of all, you mentioned that there's a big advantage using RISC-V in terms of cutting down the cost of operations and also cutting down the cost of production.
And power.
And it's more efficient. Yeah. So can you just give a practical example for just to get an idea for the order of magnitude? Like for instance, if you want to use an HPC, small HPC cluster with RISC-V versus buying x86.
So you're talking about RISC-V implementations here, okay? Which is there are a lot of factors. So printing and chip is a very expensive process, right? If you want to print a chip like in 7 nanometers, it's tens of millions. Okay. So usually the reason we have x86 in all those large systems is because they can get them off the shelf and print in large quantities. And that's why they roll over. It's not because they're better chips, it's because they're cheaper to buy. Because they took over, they have this huge part of the desktop and server market. So I cannot give you an estimate of the cost because it depends on how many chips are being printed, how popular those chips become. So okay, so I can give you an idea. I can give you an idea. I can get you maybe give you an estimate of chip area or power consumption. And again, this is again related to the implementation. So a company may make a super efficient RISC-V, another company may less efficient RISC-V. The thing is that the architecture, the way it's designed, it allows you to create a very efficient design, something that x86. So I'm going to give you numbers because we don't have the chip yet.
So that's
but maybe you can see, you can find some numbers in the microcontroller space that RISC-V is very popular there. And you can see, for example, we had some links there that describe the advantages of why NVIDIA, for example, switched to RISC-V in the GPUs, or why Western Digital and CPU switched to RISC-V for their microcontrollers. And you see a lot of interesting stuff there. Not only the flexibility that allows them to handle abstractions or the whole modular part of the architecture, also because it's very simple design, the basic RISC-V. We actually students in the university can design especially RISC-V. It's that simple to design, which is great, right? Because if you start with something simple and optimizing it, it's simple as well. So we have there are some other designs. With more complicated CPUs out there, but not yet in the market. Again, there's a delay. It takes time to design chips. You need to design, to verify, to print them, again, and the print is very expensive. And then finally, after you're done, you bring it to the node size you want, because you want to do a test run in a very expensive, a very small node size. You print it like 14 or 38 nanometers, test it there, and then when you're really sure about your design, then you're going to print it 7 or 5 or whatever new stuff we have. So it takes a lot of time.
The Argos relation to Argos and other systems like Argos is utilized, of course, for the contraction cost and the operation cost as well. So I think there's an obvious relation with that.
But the cool thing is that because you have this flexibility, you can put it in places where you wouldn't be able to put a CPU. Like, for example, you can put it very close to the fire, or to something that has very strict power requirements or chip area requirements. And because you can customize it, you can put the CPU places that you couldn't do before. So this again changes the.
But maybe just as an engineer, you say it takes a long time. What is the indication of how long does this process take?
From designing something to printing it. So first of all, designing itself takes time, because we need, we have simulators and we have stuff, and we have FPGAs where we can test our designs there. So before something becomes part of the standard, the RISC-V standard, we need to come up with a study that shows that this actually helps and improves things. That means that we need to write software about it. We need to run the compiler, the assembler. We need to implement it in a simulator. We need to provide a proof of concept to write a proof of concept, or actually something in the FPGA to test it and say, okay, here are the numbers. This thing is better. So designing takes time on its own. It may be up to 100 or 2 years for something to be finalized. To give you even simple, even things that are not very complicated, that are outside. So, for example, one of the things we've been working on regarding security, like physical memory protection for devices, like isolating devices from each other and from the CPU. It's 2 years, and it's still, more than 2 years. We are designing, we're trying to work out the details, and it's a small, simple mechanism, okay? But because lots of people are going to use this, and they have lots of different use cases, and we need it to be compatible with another mechanism from another company and stuff like that. It takes a lot of time to reach consensus on what this specification, this mechanism would look like. So once we are done with the design phase and we have a spec and it's stable, it's frozen, we are good to go, we are really confident about it, Then you go to the chip design, to the implementation. Okay, you have this, you got the document, and now you're going to put it in your chip. It can take, again, first you start with the implementation, with writing the code for it, RTL code that becomes the chip. Again, testing, a lot of testing under different use cases. You need verification, which is a lengthy process again to make sure that this is conformant to the specification. You need to optimize and make it work for test, make any changes you want for your that are related to how you implemented the rest of the chip. Like make it fit in your system, and then you have FPGA designs. You test it there with a slow clock. You try and run test there and profile it again back and forth to optimize and fix things and fix bugs and run more complicated tests as you go. And then when you're done with your FPGA, you're confident and you do the first tape out, you test it, print an ASIC, which is again very expensive, and you need another process. You need to take the library from the factory and compile the code with the factory library so that the results are file that the factory understands. So again, the lengthy process just to port the thing you've already written to the process, to the factory infrastructure, to the PDK that they give you, so that it is it's compatible for TSMC, for example, or global foundries or Intel fabs now. And then run a test run, get it, make a PCB for it, and you make a board with the chip on, and run tests on it. So again, it's time. And then after you give the first tape out, which probably is going to be buggy, because you'll find bugs in the ASIC, like in the process of switching to ASIC. Then you need more time to fix those bugs, and then go back to the fab and schedule another run. Scheduling the run takes months again. Like I have the design now, and I wanted to pre-print it. I have to wait a few months for it to be on the line. Even if I have the money to pay. And to give you an idea about the money, if you want to be parts, you don't use the whole wafer. Using whole wafer means like lots of chips. Probably you don't want to do tests, so there are multi-project wafers that people use. So you have to wait for other projects to come up, so that you can take a small part of the wafer along with every other else that takes part of the wafer. And once like the wafer is okay, they have a full wafer, then they go for print. And getting a part of the wafer may cost like a few $100,000 of euros for high node, like for 14 node size, for 14 nanometers, the one we used for our test chip. I believe it was around 200,000, something like that. For I believe 100 chips. I'm not sure. I don't remember the numbers. But again, back and forth takes months. So from experienced teams in this, that they have done this before, they know how this thing works, and they have the connections, and they have the money, it can take up to 2 years from the design, from the beginning of the designing phase to having an actual chip out there. And this is a very, optimistic estimate. So if you see here the timeline of what we have. So for example, in 22, we started working on crypto vectors, for example. Okay, we get crypto acceleration for, SSL and things you use for communicating with the website or for encrypting your hard disk. Okay, we got discovered, but now the spec was done, but we won't see any chips with that until 2025 at best. Okay, so we have lots of cool stuff. We have vectors from 2021. We still don't have. We have like 1 or 2 CPUs that use the vector extension, and they're not really yet. They're still being worked on. So and the manipulation. There we really need the manipulation structure. Very useful for lots of reasons. But again, what we did in 2021, we may see another chip on 2023. we may see it under ideal conditions. So 2 years, I believe, is a rough estimate, a very optimistic one for the whole, including the whole process for experienced teams. Right?
It's not too bad.
It's not too bad, but again, when you've gone through the whole process of designing the spec and you say, yeah, fine, we have vectors, when you don't, you will have vectors in 2 years from now. So when you're really passionate about it, then you still have to wait 2 years.
So how does the usage of RISC-V impacts on the code development at high level? You're designing a program or an image processing algorithm in, let's say, Python. Do you have to take into account that the code will run
if you're using an interpreted language like Python, nothing changes from you. You run your program as you ran it before. The Python implementation will change.
Okay.
And basically the Python interpreter, you have to recompile it, obviously, for the RISC-V architecture. And then you need to optimize it for RISC-V architecture. Optimizing means that the compiler will generally give you C, it will give you assembly, general stuff. Because RISC is very efficient, actually, it's not that bad. You don't really have to write things by hand. But when you really want to optimize something and you need to make it very efficient, and you want to play some tricks there, some algorithmic tricks, or use some extension of the CPU that the compiler does not automatically take into account, then you, like crypto, for example, the compiler will not generate crypto instructions for you. You'll have to put them there by hand. Then you need to, write handwrite assembly. So we are slow. There is a community of people working on that. There is a community of people that works on the compilers a lot and keeps optimizing them. There are people working on binary translation. There was actually last week we had a keynote in FOSCOM, a conference we organized. We had a keynote regarding binary translation of RISC-V, which basically allows you to run binaries compiled for other systems on RISC-V. And there is a whole subject, it's a very interesting subject for lots of reasons. But you basically you need to recompile it. You have a C program, Python program, you recompile it, it works if it's user space. You have to do more work if you're on an operating system, because then you need to work with privileges, you need to work with privileged instructions, you need to treat the state of the CPU, and not just the compiler, that's the instruction stream, let's say, of your application. You need to do more. And then when you move to higher, or lower, it depends on how you see the privilege tree. If you go closer to the hardware, let's say you go to firmware level, and then again, it's pretty much custom. A lot of, you have the compiler there, but you need to assist with the handler with primitives and assembly, like for the interrupt handler, how to return buffer, how to, and so if you're writing applications, you don't really care about this, you just recompile it, it works. It may not work fast. If you want it to work fast, then yeah, you need to dig in and use write some special code there. If you're writing an operating system or firmware, then yes, you need to tweak a lot of things. Not that many drivers that are going for peripherals, they remain the same. It's basically, the management of memory, of virtual memory, how you isolate processes, how you switch from how you do the system call, how you switch from the user to the operating system, and back. So stuff like that. But in general, it should be transparent to the users. I mean, think of if you're already using a Mac with an ARM chip, and a few years back it used to be an x86 chip. Was it really hard the transition for the users? Yeah, there are incompatibilities there, but I mean, for the general use case, you basically recompile your code and it works. It may not work that well, or may not be that fast, but it's not that hard to switch, right? Especially if you have something like Python or Java. So, for example, in order to get Java working properly, it's a pain because we needed some hardware assistance there. But we still don't have it. 2025 will have faster Java than we have now. It takes time, but
Speaking of Java,
Yeah, we do, yeah. No, it's very, I mean, Android, really. It's very popular, The web lab, web assembly now, there are lots of things we need to support. Very interesting stuff, very fun to work with those people. So I hope I answered your question. It shouldn't be, I mean, normally you just recompile. If you want to optimize, then yeah, you probably need to upgrade some stuff. But there are people that are doing this, at least for core libraries, like things that you use for, I don't know, Blast, for example, people will deal with it. OpenSSL for crypto, they're already put them the optimizations to there. So, and the Linux kernel, it's a large community of people. I'm working on that too. I'm going to use the kernel for adding functionality related to this file, and lots of people are working on that. So you don't really need to worry about this. Keep writing your code and let us handle the whole, the lower parts of the stuff.
Okay, thanks.
Sure.
Thanks
Okay.
again. Yeah.